Hello student, this is Usha from G.k.Jain High Secondary School. Today we are going to see atomic and nuclear physics in 12th standard physics. In this we are going to see about the Millikan oil drop experiment. Let us move on to the topic. Determination of charge of an electron, Millikan oil drop experiment. Millikan oil drop experiment is another important experiment in modern physics, which is used to determine one of the fundamental constant of nature known as charge of an electron. So this is a diagram shown over here. By adjusting the electric field suitably, the motion of the oil drop inside the chamber can be controlled. That is, it can be made to move up or down or even kept balanced in the field of view for sufficient long time. So you can see that in between you have a plate light source. So using atomizer, when the oil drop enters, using your magnetic field we are able to make it to be in the same place or move up or come down. The experimental arrangement is shown. The apparatus consists of two horizontal circular metal plates A and B, each with a diameter around 20 cm and separated by a small distance 1.5 cm. The two parallel plates are enclosed in a chamber with glass walls. Plate A and B are given a high potential difference around 10 kW such that the electric field acts vertically downward. A small hole is made at the center of the upper plate A. An atomizer is kept exactly above the hole to spray the liquid. When a fine droplet of highly viscous liquid, you can take glycerin, is sprayed using atomizer, it falls freely downward throughout the whole of the top plate, only under the influence of gravity. Few oil drops in the chamber can acquire electric field because of friction with air or passage of X-rays in between the parallel plates. Further, the chamber is illuminated by light which is passed horizontally, and oil drop can be seen clearly using microscope placed perpendicular to the light beam. These drops can move either upward or downward. Let m be the mass of the oil drop and q be its charge. Then the force acting on the droplet are, there are four things. First one is gravitational force Fg, which is equal to mg. Next is electric force Fe, which is equal to Q into E. Third one is buoyant force Fb and your viscous force Fv. Right? These are the four forces which are acting. Determination of radius of the oil droplet. So when the electric field is switched off, the oil drop accelerates downward because the acceleration due to gravity is acting in the downward direction. Due to the presence of air drag forces, the oil drop easily attains its terminal velocity and moves with a constant velocity. This velocity can be carefully measured by noting down the time taken by the oil drop to fall through a predetermined distance. Stokes method, we have done this. The free body diagram is shown over here. We note that the viscous force and the buoyant force balance the gravitational force. Let the gravitational force acting on the oil drop downward be Fg is equal to mg. Let us assume that the oil drop to be spherical in shape. Let ρ be the density of the oil drop and r be the radius of the oil drop. Then the mass of the oil drop can be expressed in terms of its density. Rho is equal to m by v. We know that density is equal to mass by volume. Now you substitute for the volume since it is in the spherical in shape. So we will take the value, that is the volume of the sphere, v is equal to 4 by 3 pi r cube. Substituting the value will get m is equal to rho into 4 by 3 pi r cube. The gravitational force can be written in the terms of density as Fg is equal to mg, which is equal to Fg. Now you substitute the value for m, so you will get rho into 4 by 3 pi r cube into g. Let sigma be the density of the air. Then the upward force experienced by the oil drop due to the displaced air is Fb is equal to sigma into 4 by 3 pi r cube into g. Once the oil drop attains a terminal velocity v, the net downward force acting on the oil drop is equal to the viscous force acting opposite to the direction of the motion of the oil drop. From Stokes' law, the viscous force on the oil drop is, we have learned in 11th standard the viscous force formula. So Fv is equal to 6 pi r V into eta. From the free body diagram, the force balancing equation is Fg is equal to Fb plus Fv. So rho into 4 by 3 pi r cube into G is equal to sigma into 4 by 3 pi r cube into G plus 6 pi r V into eta. Taking the rho into 4 by 3 pi r cube into G to the other side, we'll get 4 by 3 pi r cube into rho minus sigma into G is equal to 6 pi r into V into eta. So cancelling by 2 times, here the 3 times, 4 will 2 and 6 will be 3 times by using a 2 table. So you will get 2 by 3 pi r cube into rho minus sigma into G is equal to 3 pi r into V into eta. From this, r is equal to 9 eta V divided by 2 into rho minus sigma into G the whole power 1 by 2. Using this equation, we are able to get the radius of the oil drop. Determination of electric charge. When the electric field is switched on, the charged oil drop experiences an upward electric force which is nothing but QE. Among many drops, one particular drop can be chosen in the field of view of microscope, and strength of the electric field is adjusted to make that the particular drop to be stationary. Under these circumstances, there will be no viscous force acting on the oil drop. Then, from the free body diagram as shown earlier, we can say that the net force acting on the oil droplet is Fe is equal to, Fe plus Fb is equal to Fg. So substituting the values, we get QE plus 4 by 3 pi r cube sigma G is equal to 4 by 3 pi r cube rho G. Taking the second term to the other side, so you will get QE is equal to 4 by 3 pi r cube into rho minus sigma into G. So Q is equal to 4 by 3E into pi r cube into rho minus sigma into G. Then you will get Q is equal to substituting the value, we get Q is equal to 18 pi divided by E into eta cube V cube divided by 2 into rho minus sigma into G the whole power 1 by 2. Millikan repeated this experiment several times and computed the charges on the oil drop. He found that the charge of any oil drop can be written as integral multiple of an basic value, and the value is given as minus 1.6 into 10 power minus 19 coulomb, which is nothing but the charge of the electron. Hi students, you all have learned about the Millikan oil drop experiment. Let us meet you in the next video. Thank you.